All right, Unit 9, Notes 3, Practice Problem. Starting off with problem number 1, it says, explain what is happening in both pictures using the terms net force and acceleration. Well, in the bottom picture, obviously, you can see that these two people are going to be pushing in opposite directions, and these arrows represent their force vectors, or kind of like how strong their force is. So for this question, it's asking us to use net force and acceleration. So I'm actually going to decrease the font size here so we have a little bit of room. The net force is 0 because the forces are balanced. If the net force is 0, this means the object is not accelerating. So there is no acceleration, basically, right? So that's basically what we're saying. This object is not moving, and you can kind of have guessed that based on just what you're seeing here and from your personal experience. In this next picture over here on the right side, obviously these two people are going to be pushing the same direction now, which is more effective if they want to be moving the couch. So over here, the net force is unbalanced and is equal to, let me start a new line, the sum of the forces. Okay, the object will accelerate towards the left. If you wanted to throw in the term static in there, you could say, let's go ahead and type this again. Static friction will be first, followed by sliding friction. So let me go ahead and move that. All right, and the reason why you don't have both at the same time is because static means that it's still, and sliding means that it's moving across. So if it was still at first, that's going to be the stronger friction to overcome. And once they get those two pushing, the sliding friction takes over, and it's going to be less than the static friction. All right, so there's number 1. All right, number 2 says, come up with a specific example of something you use that is used to reduce friction and explain why it is useful in this situation. Well, you can come up with your own example if you want to, but the example that I'm going to use is wheels on a car or a cart. I guess in the first example of a moving object, like a big wagon or something like that, they had to put wheels on it. At some point in history, the invention of the wheel helped move stuff around because it was reducing the friction. Wheels reduce the friction from sliding friction to rolling friction. So remember, we said in the notes that rolling friction is usually lower than a sliding friction. So putting wheels like on a car or a cart or anything that basically you're dragging across the ground, you're going to be reducing the friction if you just put wheels on it. Number 3 says, now explain an example that increases friction and explain why it is useful in this situation. So what we could do is use rubber wheels instead of steel wheels. Changing the material can change the friction. So obviously we also discussed that sometimes you would want to increase the friction between two surfaces. For instance, if you have rubber wheels on a car, you will be able to stop at distances much faster than if you were to have just like steel wheels against the asphalt. So there are instances where we would want to increase friction and not only decrease it. All right, so there's numbers 2 and 3. Number 4 says, what is the acceleration of the car in the picture below? Okay, so let's first jot down what our data points are. So at first we have mass 5 kilograms. So that's kind of in the data section already. I don't think we have to rewrite that. Mass is 5 kilograms. And we have a force. So this is a measurement of force. Force is equal to 10 newtons. And this is asking us, what is the acceleration of the car? Well, like we mentioned in the notes, there is a very important equation that we'll need. And that equation is force is equal to the mass of an object times its acceleration. Right, so if we follow that uh, formula, we're going to rearrange it so that we're solving for acceleration. Acceleration is therefore going to equal force divided by mass. Right, so the problem was asking what is the acceleration. That's why we're solving for it. So acceleration is the force, which was given to us, 10 newtons, divided by the mass, which was 5 kilograms. And newtons and kilograms are the correct unit for this. So the acceleration, therefore, is going to equal 2, and then the unit for acceleration is meters per second squared. So there's your answer for number 4. Number 5 says, what is the acceleration of the car in the picture below? So we're doing the same problem, but in this case, we have something else. We have the car going at 10 newtons, and then we have like a parachute slowing down the car at 7 newtons. This is not a balanced force, so it's going to be moving in this direction. You have to actually add these up. So if this is positive 10 newtons, let's say this is the positive direction, and this is the negative direction. We have positive 10 newtons, negative 7 newtons. You're going to have a final unbalanced net force. So the net force is 3 newtons. Let's go ahead and actually write that down in the data. The net force is 3 newtons. All right, and then we have a mass of 6 kilograms. And then we know the formula F is equal to ma. And again, we're solving for acceleration. So we could just use A is equal to F divided by m. So A is equal to the force, which is 3 newtons, divided by my mass, which is 6 kilograms. So if we do the math there, acceleration is equal to 0.5, 1/2 meter per second squared. All right, so there's numbers 4 and 5. Okay, let's move on to number 6, which says calculate how much extra force is needed to push the van in this example. All right, so we have a person that is pushing a car and a person that's pushing a van, and we know that the car weighs 1,000 kilograms, the van weighs 2,000 kilograms, and we want to accelerate to 0.05 meters per second squared. So we know the mass in this equation. That's going to be 1,000 kilograms. And we know the acceleration is going to equal 0.05 meters per second squared. I know up here it says meters per second, but you could just rewrite that as meters per second squared. And we want to calculate that force, which is mass times acceleration. So force is equal to 1,000 times 0.05. If I did that into a calculator, I get a force that equals 50 newtons. Right? But over here, the mass is 2,000 kilograms. And the acceleration is the same, 0.05 meters per second squared. So over here, you do the same equation. F equals ma. F is equal to 2,000 times 0.05. And over here, you get a force that equals 100 newtons. Okay, so how much extra force did you need to push the van? You needed an extra 50 newtons, because that's the difference between 100 and 50. All right, so you needed 50 additional newtons to be able to push the van. So we have a question here on the bottom that says, if the minimum amount of force is used to push the car and van, which will have the higher velocity? So there's a couple of ways I can kind of interpret this question. So minimum amount of force is used to push the car and van. If we're talking about the minimum force for the car and the minimum force for the van, so each one would have the minimum. Let's say the minimum force is the same for both. Okay, so it's the same force. Let's say that value has to be 50 newtons. Okay, so if both of these were able to be pushed at 50 newtons, like eventually you could get this pushed at 50 newtons, then that means that the car would have a higher velocity. And the reason for that is because we know that force is equal to the mass times the acceleration, right? So if force is the same for both scenarios and mass is lower for the car, that means acceleration has to be higher. And since acceleration is higher, that means it's changing its velocity faster. Because remember, acceleration is nothing but a change in velocity. So kind of give you an example of that. Let's say the force was 50 newtons for both. And for the first car, let's say that weighed 10 kilograms. Just for fun, we'll say it's 10 kilograms, which is about 22 pounds. All right. That means it would accelerate at 5 meters per second squared, right? But let's say that the the van rather, weighs 25 kilograms. It weighs over double. Well, that means it's accelerating at 2 meters per second squared. So what that means is that if the force is the same and you decrease the mass, it's going to accelerate faster. So if the minimum force is the same for both of these, the car would have the higher velocity. That's the first way you can interpret this question. The second way you can kind of interpret this question is, well, if it's the minimum force for the car and the minimum force for the van, and it's separate, they will both be accelerating at the same rate. So it's proportional, right? So we didn't change the acceleration for both of these. I'm going to go ahead and just highlight here. So we have 0.5 or 0.05 and 0.05 there. So what that means is that they're accelerating at the same rate. And since they're both accelerating at the same rate, they're both changing their velocity at the same rate. So neither one would have the higher velocity. You would need more force in order to push the van because it weighs more. That's the only reason why you would need more force. But they are accelerating at the same rate, meaning they have the same velocity. So two different ways you can kind of interpret this problem. The first way, just to review, if you had the minimum force and the force was the same for both, the car would be going faster because it weighs less. But if you had separate forces, so that it was the minimum for the car and then the minimum for the van, the speed would be the same because the force is only proportional to their mass. Number 7 says, what is the mass of an object that requires a force of 30 newtons to accelerate at a rate of 5 meters per second squared? So go ahead and start this problem by writing down all the things that you have. You have a force of 30 newtons and acceleration of 5 meters per second squared. And we know the equation of force is equal to mass times acceleration. In this case, we are solving for the mass. What is the mass? So mass is equal to mass is equal to force times, or force divided by acceleration. All right, so let's go ahead and start plugging in numbers. Mass is equal to 30 newtons divided by 5 meters per second squared. So in this case, mass, used to writing force, mass is equal to 6 kilograms. All right, so that was an easy one. Number 8 says, what is the acceleration of a 6.4 kilogram bowling ball if a force of 12 newtons is applied to it? Okay, so we have 6.4 kilograms, that's our first value, and then 12 newtons. And then we have to identify these. This is a mass, and this is a force. And the question is asking for, what is the acceleration? Do we know acceleration? Not yet. We do know this equation, and we know that we could rearrange it so that it looks like this. Let me just fix that. Force divided by mass. So I just rearranged this so that it looks like that. And then I'm going to start filling in numbers. So I have 12 newtons divided by 6.4 kilograms. So I'm going to go ahead and put that into the calculator. 12 divided by 6.4. And I get an acceleration that equals 1.875 meters per second squared. All right, so there's number 8. Finally, number 9 says, what is the acceleration of a 2,000 kilogram truck if the force of 4,200 newtons is used to make it start moving? Okay, so we have 2,000 kilograms and then 4,200 newtons. So this is a mass, this is a force, and we need acceleration because that's what the problem is asking for. What is the acceleration? So force is equal to mass times acceleration. We know this, and we're solving for acceleration. So let's rearrange this just like we did before. Acceleration is equal to force divided by mass. So acceleration is going to equal my force of 4,200 newtons divided by 2,000. So if I put that into a calculator, I get 2.1 meters per second squared. Alright, so that concludes the practice problems for Notes 3. I'll see you in Notes 4 when we talk about Newton's third law.